Hi and welcome to the second part of this video tutorial. In this part I want to talk about data flow operations, abbreviated DFOs, and data flow operation trees, abbreviated DFO trees. For two reasons I want to cover this topic with a separate part of this tutorial. First, this topic is probably not really that much covered anywhere else, and second, it's important to get an understanding of that concept in order to understand some of the effects that I will demonstrate in the upcoming parts of this video tutorial when doing the actual analysis of parallel execution skew. So, these are all of these things are specific to parallel execution, so you don't find any counterpart in serial execution plans. So what can we say about data flow operations, about DFOs? First of all, a parallel execution plan consists of at least one or more data flow operation trees. Sometimes you might also hear the term parallelizers in that context, which seems to be a newer term for the DFO tree. So a parallel execution plan consists of one or more DFO trees. That's the first thing to understand. So as soon as you have a parallel execution plan, there is at least one DFO tree. And if there is only a single one, then you probably can simply ignore the fact that you deal with a DFO tree, because the side effects and implications about DFO trees become only relevant when we deal with more than a single one. Then, if you happen to have multiple DFO trees in a parallel execution plan, then you can have them in a parent-child relationship, which means that it's not necessarily a parent-child relationship. They could also be below a common root, so that not one DFO tree is a child to another DFO tree, but they all belong to the same root. So it's possible that you have DFO trees that are related to each other in a kind of parent-child relationship, but it's not necessarily the case. So that's another thing to consider, and I will show you examples shortly which make this more clear, what I try to express here. Then each DFO tree consists of one or more data flow operations. So that's basically the idea that one or more data flow operations form a DFO tree. At minimum you will have a single DFO, but a DFO tree can of course have many DFOs. And what is a data flow operation? In principle, the data flow operation is a unit of operations in the execution plan that are based on the same data distribution. So with parallel execution we always have the challenge to distribute the data across the parallel execution servers so that we can actually do things in parallel. And all the activities that can be performed without having to redistribute the data basically can then form a single data flow operation. And if we need to redistribute data, then we will have a parent and a child data flow operation, and these DFOs will then exchange the data, communicate via so-called table queues, and these are also sometimes called virtual tables. But I think table queues is the more common term. So table queues are a kind of a memory construct that can be used by the parallel execution servers to talk to each other to exchange the data for redistribution. And of course, if you think of a rack, of a cluster with several instances, then table queues do not only communicate via memory, but the data needs to be exchanged via the interconnect, via the network. So before I go into the details, because this is now a lot of theory and I also don't have any nice pictures drawn. So before I show you actual execution plans to show you the different flavors of DFO trees that you can get with parallel execution, just a couple of implications. The first thing is that each DFO tree has a serial root operation that is shown in the execution plan with this PX coordinator operation. So that's one important point. So each DFO tree starts with this PX coordinator, and this operation is a serial operation. So depending on what the actual plan shape looks like, this might already have some significant influence on the overall activity at runtime, because imagine you have a very large amount of data that needs to be piped through this serial part of the execution plan, and if you get unlucky, then maybe Oracle also tries to compute something in this serial part, then you actually might spend a lot of time in that serial part of the execution plan. So that's one important point to consider, that each DFO tree has this serial root operation. It's not necessarily a problem, as I said. It depends on the plan shape, but it's something to keep in mind. Then another thing to consider is that for each DFO tree, the degree of parallelism will be determined by the optimizer. So in theory and also in practice, it is actually possible to arrive at different degrees per DFO tree. So this also means that if you happen to have a parallel execution plan with multiple DFOs, multiple DFO trees, then there is a chance that you actually have more than a single degree of parallelism in a single execution plan. So some part of this execution plan might be executed at a degree of 4 and another part at a degree of 8. That's perfectly possible. And it's just that the unit where the degree is determined is the DFO tree. And therefore, if you have multiple DFO trees, it's possible to end up with different degrees determined by the optimizer. Then at execution time, there is one very important implication. Each DFO tree in most cases gets its own parallel execution servers. So consider that you have two Dataflow Operation trees, two DFO trees, and each have the same degree of parallelism, let's say 8, and each DFO tree has multiple DFOs, so that you end up with 2 sets of parallel execution servers per DFO tree. This means that you might end up with actually 2 times the number of parallel execution servers that you would expect. So because usually one says that if you have a degree of 8, then you have this rule of thumb that you at most will have 16 parallel execution servers active due to these 2 sets that will be allocated. But with multiple DFO trees, you can actually end up with many more parallel execution servers. So because each DFO tree usually gets its own parallel execution servers allocated. This has also a very important implication if you think about restricting the degree using the resource manager. The resource manager can limit the actual degree of parallelism that gets used at execution time, but it actually cannot limit the number of parallel execution servers that get allocated to a single parallel execution, simply due to the fact that you can have as many DFO trees as you like, and therefore it's perfectly possible to run out of parallel execution servers even with the resource manager plan active, if you have an unlucky parallel execution plan that has many DFO trees that are allocating the parallel execution servers in such a way that that they are actually required concurrently. So that's also something that probably is not that well known. Then, depending on the execution plan shape, DFO trees might be started just once, or they might be started multiple times. And this is probably something typically if you end up with an execution plan where DFO trees get started multiple times, then in the majority of cases it's probably a sign of a rather inefficient execution plan. So that's also something to keep in mind. If you end up with something where DFO trees get started multiple times, then you should check very carefully whether this execution plan really makes sense or not. Why is this a very probable sign of inefficiency, this multiple starts? Because usually each time a DFO tree starts, it reacquires the parallel execution servers for its execution. So consider that you might have something that is started thousands of times. Then basically each time the DFO tree starts, you will have this overhead in the query coordinator activity that it needs to reacquire the parallel execution servers. So it's perfectly possible to spend actually more time in that overhead trying to coordinate and acquire these parallel execution servers than actually doing anything useful in the actual activity that is then following this reacquisition. So that is one of the main reasons why having a DFO tree started multiple times is a bad idea. It also has another interesting implication that if you have multiple DFO trees, even if you don't have different degrees determined by the optimizer, you still might get a downgrade at runtime because you, for instance, let's say you have multiple DFO trees and these are not active concurrently but one after the other, which is also perfectly possible depending on the execution plan shape. Then maybe although the same degree was requested by the optimizer at execution time, you might have the problem that at the start of the first DFO tree there are sufficient number of parallel execution servers available, whereas when the second DFO tree starts and acquires its parallel execution servers, it runs out of the parallel execution servers. The pool is not able to provide sufficient number of parallel execution servers, and you will get a partial downgrade basically. So you have some part of the execution plan executed at the desired degree and another part of the execution plan might be executed with a different degree simply due to a downgrade. And then just another effect that is more in terms of instrumentation and diagnosis and diagnostics interesting, that is that typically for each DFO tree you get a separate child cursor at runtime. So if you happen to have 5 DFO trees, then you actually get 5 child cursors, and that has some interesting side effects. For example, if you try to use DBMS display, DBMS X-Plan display cursor, then or if you even real-time signal monitoring is confused up to the latest versions available up to 12.1, you still get sometimes confusing results simply due to the fact that there are multiple child cursors and not all of the code really copes very well with the fact that you have for a single SQL execution multiple child cursors. Right, so I think we are almost done with the theory. Just to wrap things up, another interesting point to understand is that it's not really desirable to have multiple DFO trees. So it's simply a result of a limitation in the optimizer. So it would be great if we just could ignore all the side effects of having multiple DFO trees, and a parallel execution plan would simply consist of a single DFO tree. But in reality, we have to. But in reality, we have to deal with this. That depending on what kind of SQL gets used, the optimizer starts to decompose the parallel execution plan into multiple DFO trees. And this actually hasn't changed much, with just some minor variations. This hasn't changed much for the recent releases and recent years even. So version 10 or 11 didn't really introduce a lot of news with regard to that. So you still would have the possibility of having multiple data flow operation trees, multiple DFO trees. But the good thing is that with Oracle 12c, finally Oracle has started to address these issues. So many of these limitations that were in previous releases that led to this generation of multiple DFO trees have been addressed with 12c. So we will see right now in the demo that 12c shows in many cases different plan shapes than previous releases. So that should be enough theory. Let's have a look at a couple of examples that I've prepared, so you can get an idea of what kind of different plan shapes we can get, and different number of data flow operation trees, DFO trees, and data flow operations, DFOs, and so on. Let's have a look at that. Right, so let's start with a simple example here. This is a typical parallel execution plan. So we have a single DFO tree, and this single DFO tree consists of many data flow operations, simply because the data needs to be redistributed several times, and only what can be done without data redistribution, these operations together then form one data flow operation, or one DFO node in the DFO tree. So first thing, let's go to the execution plan. This is actually the output from XPlan-Ash, the tool that I have developed and still maintaining, in particular to analyze parallel execution, but it can also be used for serial execution. Let's go to the plan details, the execution plan output, and how do we then know whether we deal with a single DFO tree or multiple DFO trees. So the one thing that is quite obvious, it's very simple to check how many of these PX coordinator or operators you have in your parallel execution plan. So as we can see here, there's only a single one, so we deal with a single DFO tree. That's one way you can determine how many DFO trees you end up with. Another way you can determine this is this table queue information that you only get with parallel execution plans. You have this Q1 here in front, and actually this 1 here, so the digit after the Q, is the DFO tree number. So as we can see, as we only find here Q1, this is another indication that we have a single DFO tree, as we will see with other examples where we end up with multiple DFO trees. And actually the number after the comma is the number that denotes the DFO. So what does it mean to have a DFO? So we can have a look here what makes a single DFO. So anything that has the same number here basically forms a DFO. So we can, for example, see that this DFO here, this data flow operation, is just this full table scan, and that gets immediately basically redistributed. So there's not much done within this single DFO node. we can see here also this concept that we have these table queues where these two DFOs communicate. So we have one parallel execution server set active that is running this DFO node here. That is in this case here the producer part. So this one here, this DFO produces data, and we see here with this px receive operation another DFO that is the consumer part that is receiving the data. We can see that in this case here we have some other operations that are forming this DFO here. We have here another consumer part for this data flow operation, where it actually gets data sent from another DFO. So that is another parent-child DFO relationship here, where data gets produced and consumed. So this DFO here is the parent to two other DFOs and is then responsible for performing this hash join here, and then we'll hand over the data again to another DFO that we can see here has the number 7. That is basically the relationship with DFOs. So we have parent and child DFOs. They communicate via these table queues here, and that is necessary to redistribute the data for parallel execution. And if you want to get an idea of the actual order of operation of a parallel execution plan, then you can use a very simple rule that is follow the table queue numbers basically. So this parallel execution plan will actually start here with this DFO 0, and it will be active together with this DFO here that receives this data. Then the next one would be here this DFO 1, which is again sending to the same parent DFO the data. Then the next one would be this here, number 2, and so on and so on. So that is basically the flow that you can see with the parallel execution plan that will happen. And these multiple DFOs here form then this DFO tree. So you have if you want to think of a tree, then we have here multiple leaves, multiple branches, and then basically this single root here, this px coordinator, where everything starts. So that is a typical parallel execution plan where you have multiple redistributions, and these redistributions are done by having parent-child DFOs active that exchange or that send data from a producer to a consumer part. That is basically the idea behind this parallel execution plan. Right, so and as long as we have that single DFO tree, you don't have to worry about side effects of what does that mean that you have a DFO tree. It can be simply ignored. So let's have a look at another execution plan where we end up with multiple DFO trees. So this is probably the most common way you actually end up with multiple DFO trees, and it's probably also the least harmful way of having multiple DFO trees. That is, if you end up with parallel temp table transformations. Usually if you use the with clause, the common subquery expression in your SQL, and you use parallel execution, then these materialization of intermediate results that is possible with the with clause, this can happen in parallel. And then in this case you end up with actually multiple DFO trees, because each temp table transformation forms its own DFO tree. This has the nice side effect that these DFO trees are actually active one after the other. So they are not actually active concurrently, but the first temp table transformation is done, then the second one and third one, and so on. So each DFO tree is active on its own and is not active at the same time as the other DFO trees, and therefore this kind of having multiple DFO trees is not really that much of a threat. This also means that although I said that each DFO tree acquires its own set of parallel execution servers, in this case here Oracle is usually clever enough to basically reuse the previously used parallel execution servers. So when one DFO tree is complete and the next DFO tree starts, let's see for example this one here, you see here this first DFO tree here, and you can see here that we have then multiple PX coordinators, and you can also see here confirmed that you have here this 1 after the Q following, and you have here this 2 following in for the second DFO and 3 for the third DFO and so on. So this is how you can identify the different DFO trees. So when this DFO tree here is complete, this one, then the next one will start here, this DFO tree number 2, and it will reacquire the parallel execution servers and typically will then reuse those parallel execution servers that were used here for executing this DFO tree. So this also means although you have multiple DFO trees in this case, it does not necessarily mean that this kind of execution will use more parallel execution servers than you expect, because they are not active concurrently. So although this reacquisition happens, you still have only, let's say, each DFO tree operates at a degree of 8, then you have at all time at every time during the execution you have at most 16. If you have 2 sets, then you have at most 16 parallel execution servers active, and not 2 or 3 times 16 due to the fact that you have multiple DFO trees. So this is a good thing about these plan shapes where you have these temp table transformations, that one DFO tree is active after the other. In this case here we can actually see the effect that each DFO tree gets its own degree determined. If we look closely here at this XX column from the real-time SQL monitoring information, then you can see here that these operations here were executed obviously at a degree of 2, and this DFO here, this DFO tree uses a degree of 15, and in the xplan-ash output we could get this also confirmed here because I use a separate section that shows a summary per Dataflow tree, Dataflow Operation, that shows a summary per DFO tree, and we can see here confirmed that the actual degree used at runtime was a different one, and in this case it was not a downgrade, it was basically a deliberate decision by the optimizer that for the first DFO tree it came to the conclusion to run it at a degree of 2, whereas for the DFO tree 2 and 3 it used a degree of 15. So as you see here, it's actually possible to end up with different degrees determined by the optimizer, and then you also see a difference in activity that part of the execution plan here is then running at this degree of 2, and another part of the execution plan is running at a degree of 15. So that's possible, and it happens. So that's something to consider. That's basically the only threat that you have with this variation of having multiple DFO trees that each DFO tree might get a different degree. Now you might say, no, all of my objects are using a default degree or using the same degree, so they should all run at the same degree, so I don't really have to bother with this different degree thing. Then you have to remember that I said in the beginning that when a DFO tree starts, it will reacquire or acquire its parallel execution servers. So although you might have the same degree across all DFO trees, when this DFO tree here ends and this one starts, you might still be in the situation that you get a downgrade for this DFO tree. So even if you have the same degree determined by the optimizer, these different DFO trees might at runtime run with different degrees, simply due to the fact that you get a downgrade when the DFO tree initializes. So that's just another thing that you need to keep in mind if you ever wonder why you might see different degrees at runtime. If you have multiple DFO trees, then it might happen that you get a partial downgrade, so that some or one of the DFO trees of the execution plan, when acquiring its parallel execution servers, gets downgraded. Right, so then let's look at another shape. This one here is now one where we again have multiple DFO trees. Of course, that's the point of this tutorial here. So if we look here, this is a PX coordinator here, but now we have a different shape. We have now here a PX coordinator right in the middle of the execution plan and another PX coordinator here. So in contrast to the previous one with the temp table transformation, with the temp table transformation you typically don't have this parent-child relationship between the DFO trees. So if let me just go back to the previous plan, you see here these PX coordinators are all on the same level. So one PX coordinator is not a parent to another PX coordinator. So they all have this common temp table transformation root, which is in my eyes, by the way, I think a bug, because this main execution here after the temp table transformation should actually be a child of the select and not a child of the temp table transformation. But that's not really relevant now. You just wanted to mention that. So we have here these PX coordinators are not related to each other as in a parent-child relationship. Whereas with this execution plan here, we have multiple Dataflow Operation trees. We have multiple DFO trees here and here and here. So we again have, as we can see from this Q1, 2, 3, we have 3 DFO trees, but this time they are actually related to each other in such a way that one DFO tree is a child or a parent to the other one. And now you have this very important point to consider, that that I said that each DFO tree has this serial PX coordinator root. So the data now here definitely has to flow through. The data here now has definitely to flow through these serial parts of the execution plan. And typically this is something that you do not want, because parallel execution is usually about processing large amounts of data, and you don't want to pipe your giga or terabytes through a single process. So that is here definitely something that will affect the scalability of this parallel execution. To what degree it affects the scalability depends on what you actually do in these serial parts. Here in this case, I think we might actually have the problem. No, it's not that relevant here in this case. There's not so much activity in that serial part, but I often have come across cases where then some unlucky execution plan ended up with doing some, for instance, calling some PL/SQL functions that were quite costly in the serial part of the execution plan. So then you really have an exaggeration of this problem, that you basically have a parallel execution plan, but at runtime actually spend most of your time in these serial parts. So that is one possible side effect of this parent-child DFO tree stuff, that you have these serial parts where your data has to flow through, which will, as I said, which will give you some problems with the scalability, because you have to process the data in these serial parts. But it might not be that bad if you simply need the data to flow through this serial part. But it's something that cannot be avoided if you have multiple DFO trees that are related parent-child. Then the data will have to flow through the serial parts. So that is something to consider, and typically something that you want to avoid. Again, in this case here, by the way, you can again see that these DFO trees even resulted again in different degrees. So this part here ran at a degree of 4, this one here ran at a degree of 8, and this one here again ran at a degree of 4. So again, it's perfectly possible with multiple DFO trees to see something like this here that we can see confirmed. Okay, so one thing I wanted to point out, that this here is actually a case, also a case where these multiple DFO trees are really active at the same time. They are concurrently active. So in particular, this part here, if we have this hash join here that is actually running in the serial part of the execution plan, but we have this part here that does something in parallel, then basically hands over the data to the serial part that is doing the hash join, and this serial hash join is then handing over the data again to this parallel part that does this data load operation here. Then this DFO here, this DFO 2 and this DFO tree number 2 and this DFO tree number 3, these will definitely be active concurrently. So this has the other implication in this case, that you will really end up with more parallel execution servers than you probably would expect being active concurrently at a degree of 4 or a degree of 8, because you have here one set active. In this case we have just a single set, because there's only a single DFO, not multiple DFOs that need to talk to each other. So we have here a set of 8, and we have here 2 sets of 4, because this one here has multiple DFOs, so it will have 2 sets. So this execution plan will have effectively 16 parallel execution servers that will be used concurrently. Although you might not expect it, and we can also see this confirmed here from the xplanash output, that we really have multiple DFOs active concurrently, and we see also that there were a lot of processes allocated for this execution. So in fact, Oracle ended up with 20 servers where we can see this from the real-time SQL monitoring information, that 20 servers were requested, and we had a minimum degree of 4 and a maximum degree of 8. That is also something that you can get from real-time SQL monitoring, but it's not part of the official real-time SQL monitoring report. It's something that is only reported by my xplanash tool. The official report only shows this maximum DOP. At least in the overview. If you click through the sub tabs of the active real-time SQL monitoring report, then you can get an idea that different degrees were used, but it's not that obvious from the official report. Yeah, so we have actually not 16 but 20 servers here that were requested. Alright, so let's look at another variation that is rather similar to the one that we have just seen, but the difference is in this case here that due to these blocking operations that are now used, you do not really have these different DFO trees active concurrently. Right, so again we can check. We have 1, 2, 3 DFO trees, and again we have a parent-child relationship, so this these two DFO trees are a child to this parent DFO tree here. But in this case here, this window buffer operator will basically buffer all data before it will hand over data to the parent operation. So and this means, in contrast to the previous plan, although we have a parent-child DFO tree plan shape, the different DFO trees won't be active at the same time, because we will start here with this window buffer will then take all the data, consume all the data basically from this first DFO tree. The hash join will build its hash table. Then this second DFO tree will be started. Again, this serial window buffer will consume all the data from this DFO tree here, and therefore will hand over the data to this view and eventually to this hash join. This hash join will do its hashing, its actual join, and then hand over to the parent DFO tree here only when this one here is completely consumed by the window buffer. So this one here won't be active concurrently with this one here above. So that's the slight difference between this plan shape and the previous plan shape. And by the way, we again have different degrees. Of course, I deliberately designed that in that way to demonstrate that it's possible. Depends on what degree you use and the plan shape, the degree you use on object level or maybe on hint level, and the other settings. If you, for instance, use the new auto degree of parallelism, then you might get here different results regarding the degrees. But as you see, it's possible to have these different degrees. So the next plan shape is again a bit different from the activity here. Let's see. This is a bit special in that sense that we have again, although we have again 3 DFO trees, we now have here no parent-child relationship. This px coordinator is, these are not related to each other in that the one is parent or child to the other one. But the special thing about this here is that we have here scalar subqueries that run in parallel. And the interesting thing in this case here is that this is seems to me a special case that the DFO trees are actually executed by the same parallel execution servers that also run this main DFO tree here. So in contrast to the previous cases where we had multiple DFO trees, you do not get this reacquisition of parallel execution servers, of separate parallel execution server sets, but this here is actually executed by the same parallel execution servers that run the main query. That seems to be something specific to parallel scalar subqueries. Maybe something that you can forget immediately again, because if you happen to see something like this in your execution plan, then it's very, very likely that you want to change something about it, because this is very, very, very inefficient. It doesn't really make sense to run scalar subqueries using parallel execution, at least if they are executed really multiple times, which is very likely with scalar subqueries. As you can see here, we have 500 executions, and it took, I don't know, I think more than 2 minutes to do this 500 executions, simply due to this massive overhead. So this really doesn't make a lot of sense, but I just wanted to demonstrate it, that there seem to be cases where this typical rule, each DFO tree gets its own set of parallel execution servers and does this reacquisition at start and so on, that this is not always the case. Yeah, we can see this confirmed here, that these things actually run parallel, that we see here that parallel execution servers were really involved in performing these scalar subqueries. Right, the next one. Yeah, this is another case of having multiple DFO trees. In this case, we can see here we have two, one here, the second one here, and again, they are not really parent-child related, so they are on the same level again. And in this case, it's a filter operation. So this is something that is usually also a sign of inefficiency. If you see something like this, that you have a filter and the second, third of nth child of the filter is a separate DFO tree, then it's again probably a sign that you want to do something about this, because again you have the problem that in this case here you have really the problem, in contrast to the scalar subqueries, that in this case here really each time the this part here starts, a reacquisition happens, and you also have separate parallel execution server sets. We can see this here. In this case here, that we really have a lot of executions, so 180,000 times this one here has been started, simply due to this filter operator here. And we can see, I think, that they even have different degrees. Let's have a look. Yeah, this filter one ran at a degree of 2, and the main query ran at a degree of 8. So these are really different DFO trees, different parallel execution servers, and you have this overhead of reacquisition with each start. So this is a highly inefficient plan. And typically, if you see something like this, a filter, and you have as second or third thing, which are these operations to the filter that get started as many times as you have rows that are here coming to the filter from the first child of the filter operation, and you only have the hope that this so-called scalar subquery caching avoids some of the executions. In this case here it did avoid some executions, so we do not have 660,000 but only 180,000 executions, but still you don't want to have this run in parallel, so that is something you want to avoid. And it's a possible plan shape, and you will have then, if this for some reason the optimizer thinks this should run in parallel, then you might end up with something like this. And of course you have, as I said, again, this is one of the plan shapes where you have the problem that there are more parallel execution servers allocated than you expect. We can see here this is a bit different here, because we have this reacquisitions with the starts, that we have here a lot of a lot of servers requested and allocated. So that is this side effect of this starting it over and over again. In fact, we can see an interesting effect here, that after several hundred of starts, somehow the operation switched from parallel Here you can see these two parallel execution servers active, and it somehow switched to the query coordinator. So like some overflow internally that happened, that Oracle stopped running this filter in parallel but switched to serial execution, which is something I can reproduce with this case here. I haven't traced it yet to understand why this switch happens, but I've also seen real-life cases where this doesn't happen, and you have really parallel execution servers being reacquired several thousands of times, and you spend most of the time in this reacquisition overhead, as I already pointed out in the beginning. So what else do we have? This is just a variation of the previous one, which has really a combination of threads. So we have here now 4 DFO trees, and we have this parent-child thing. Here a PX coordinator, here a PX coordinator, which is a child to this PX coordinator, but we also have this PX coordinator here, which is again a child to a filter operation, and it basically has the same problem as in the previous one. And when we now start looking at the improvements with 12c, then you will see why I have added this example here. But at least in pre-12c, this isn't really that different from what we have seen in the previous examples. So let's have a look at 12c. What does change? What remains the same? And maybe some other interesting side notes. So for the single DFO tree thing, in terms of handling of the DFOs and the DFO trees, there is not really a difference with 12c. So we have this single large DFO tree here with many DFOs that talk to each other via these table queues. That's not much different. The only difference probably is here that we have this new hybrid hash distribution method that is new, that was introduced in 12c. But that shouldn't bother us now in terms of DFO trees, DFOs. It's rather the same. So let's have a look at the next one, where we had multiple DFO trees. That was the one with the temp table, parallel temp table transformation. And we can see here that again here's still the same with 12c. So having this multiple temp table transformation in 12c will still lead to multiple DFO trees, and we can also see here confirmed all this 12c comes to the same conclusion. So we have different degrees in the different DFO trees. So all these things that I said before, that they are active one after the other, and basically the parallel execution servers get reacquired, but you have the threat of possible downgrades, or in principle different degrees per DFO trees. That's still the same with this plan shape, so that doesn't change with 12c. Next one. Yep. The next one was this one where we had this parent-child relation between, we had multiple DFO trees and we had parent-child relationship, where we had the serial part, where the data had to flow through the serial part. Well, this looks now quite different with 12c. The most important point to see here with 12c is that we have a single DFO. So we only have a single degree. That is a good thing. So we have only one DFO tree, and we have don't have to bother with different degrees. However, the problem of processing the data serially is in this case not really addressed, which is simply something in this case that Oracle is not capable of doing in parallel. That is applying this row num function here. which simply has to be done serially. And therefore, in order to have this single DFO tree, Oracle 12c introduced a new distribution method, which is called one-slave distribution, which means that a part of the execution plan, in this case here, this DFO, will be run by one of the parallel execution servers. So the main difference is that with pre-12c you will have this part executed by the query coordinator session itself, whereas with 12c this part is now executed by one of the parallel execution servers. So that is this purpose of this one slave distribution, which has the advantage that we do not have this multiple DFO tree stuff, so we have the single DFO tree. And it doesn't change, however, that this part is processed serially. So if significant things get done here in this serial part, you still have this scalability problem. That is not really that much different to pre-12c, but at least we do not have to bother with this different DFO tree thing any longer. So that's a good thing that 12c tries to address these limitations. Okay, so then the next execution plan is basically the same picture, in that sense that we had these in pre-12c we had this parent-child DFO trees, and we had this blocking operation, this window buffer that basically caused that these different DFO trees weren't active concurrently. Since we have now here again a single DFO tree, we do not have to bother whether multiple DFO trees are active at the same time or not. But we can see here again, of course, the same effect. In this case, this one slave ordered distribution, that this DFO here, this one, is performed serially. You can see this decorated with this not parallel combined with parent and parallel combined with child. And in this case it's serial combined with parent and serial combined with child. That's also something that is new with this one slave. You never see this in-out SC, WC or WP in pre-12c. There is no such thing. This would be performed serially, or is performed serially by the query coordinator in pre-12c. And again, this part here, which is the same DFO because it has the same number here, again this part is done serially. But at least we have this single DFO, so that's a good thing. Next one is this one is quite interesting. This is the scalar subquery variation, where the scalar subquery in pre-12c was done in parallel. And if we look at this here now, it rather looks like a serial execution, because there is no PX coordinator, and we have here this DFO tree, and here we don't have any parallel execution information. So this definitely looks like a serial execution. But it turns out that at runtime, actually parallel execution servers perform this part here. So this is one of the cases where I think that in 12c the execution plan is somehow misleading, that you think that the scalar subquery is performed serially, and the plan suggests that it's performed serially, but obviously at runtime it is actually executed in parallel. And although I see here only a single parallel execution server out of the 4, or I don't know how many are actually 4 is the degree here that could be involved, I think I've seen different cases where we actually saw multiple parallel execution servers being active in this scalar subquery part, even in 12c. So that is misleading plan shape, I think. or maybe a bug. I don't know exactly. But there's a discrepancy between what the plan suggests and the actual runtime activity in 12c. The next one was this filter thing, where we had this problem that this filter part would really run with separate slave sets, with reacquisition, with each start, and so on and so on. And this looks now quite different with 12c. The main difference is that this filter here actually runs. This filter here runs parallel. So if we look at the let's see whether I can find it. I think it should be this one here. Now that's the this is the corresponding 11.2 plan, and here you can see that the filter itself is performed by the query coordinator. So that is the main difference. There is a new feature in 12c where this filter can actually performed in parallel. So that is basically what we get from this plan here now, that we have this filter performed in parallel rather than by the query coordinator. And again, I think the plan is not really that obvious. That doesn't make that obvious what the actual runtime activity looks like. So this parallel filter here means that each of the parallel execution servers will run this filter at the same time. So rather than piping the data through the query coordinator and then running the filter, the second child of this filter operation, each parallel execution server now can run the filter concurrently, which is a very good thing and a big improvement compared to pre-12c. And we can see here this, it looks like that this filter here, that is the second child to the filter, that this operation here is run serially. But as I've just said, each parallel execution server runs this full table scan. So you could say that yes, it runs serially, in that sense that it that each parallel execution server independently from the other does this full table scan, but the activity is actually done as part of this operation. So well, I would think that it made more sense to have this decorated as this parallel combined with parent thing, because we can see here that it's, as I said, it's actually the parallel execution servers that run now this operation here. So it's not really a serial execution in that sense. So again, it's a new feature. Plan looks different. It's a big improvement that we can run now this filter stuff in parallel, and it is actually much faster than in 11.2. At least this simple case here, it's really several times faster than the 11.2 variant, but the plan looks a bit strange to me that we have this full table scan that suggests that it's run serially. And by the way, there's a new hint, this PQ filter hint, that allows to control how this filter is actually performed here. You can see here that in this case actually a hash distribution was used before this filter is then performed. Therefore we have this PQ hash hint here. There are different shapes possible. For instance, we could tell Oracle, or Oracle might come to the conclusion that it doesn't need to run this hash distribution here. So we can have different plan shapes with this new filter, parallel filter capability. Yeah, and what else do we have? Yeah, this is the final example that I wanted to show you, that I've just talked about this parallel filter capability and so on in 12c. And the interesting thing is that if you start to combine things, so here we have this parent-child DFO tree stuff from pre-12c. Typically 12c would address this here and would merge this into a single DFO tree, but if I start to combine the parallel filter, or let's say the filter, with the parent-child DFO trees, then we see here that 12c no longer uses this new feature. So now we have, even in 12c, again multiple DFO trees. We have even different degrees, I think, right? We have here degree 4, in here a degree of 8. And the filter again runs serially, so clearly there are some plan shapes possible where 12c is not yet capable of using this new features. So the message that I wanted to bring across with this example here is that although 12c addresses a lot of these multiple DFO tree issues from the past, you will see with 12c, you will still see occasionally plans where you still have this old multiple DFO tree stuff. And of course, as I've shown you in the beginning or in the middle, that if you have this parallel temp table transformation, then 12c will still have multiple DFO trees. So multiple DFO trees is addressed in many cases with 12c, but it's not completely gone. And I hope this demo here gave you an idea that depending on how these different DFO trees might be combined, you have different implications and different things to consider.